Well, good afternoon, everybody, and welcome along to Data Platform Downunder. My name's Warwick Rudd, and in conjunction with my co-host Martin Casserole, we're bringing you SQL Server internals and architecture from Kevin Klein. This session is being recorded and will be made available on our YouTube channel in a few days' time once the session has completed and we've had time to upload that. With that, I'll hand over to Kevin and we'll get today's session rolling.
Oh, well, thanks so much, Warwick. I appreciate the invitation to speak to you all. I live in Nashville, Tennessee, kind of smack in the center of the eastern part of the USA, where the mighty Mississippi River divides the country in half. I'm kind of almost directly in the middle of the country on that side of the east side of the river. And you probably have heard of country music and so forth. So that's what is Nashville's main claim to fame. Also, I do want to point out that I have a deep and abiding love of Australia, and I knew I was going to love this place, Australia, when I first got to travel at the invitation of Dr. Greg Lowe, and enjoyed visiting many different cities there. And then again, just recently, 2 years ago, with Warwick. And you know, you build a special bond with someone like Warwick and Greg when you get to crack jokes about Englishmen all day long. So you know, it was good times. So, and I'm kind of making a joke to Warwick. I'm sorry, to Martin there. So you can punch me the next time you see me, or insist I buy you a drink, right? So again, my name is Kevin Klein. I work for a company called Century One. We were just acquired a little while ago by a bigger company, SolarWinds, and my position now at SolarWinds is head geek. What a strange title that is. You can reach me at any of those connection points there: email, Twitter, LinkedIn, and I'd be thrilled to share the slides with you if you want to see the notes pages, or if you would like to get a copy of any of that kind of information.
Kevin,
So,
do you just
yes, sir.
Do you just want to share your slide deck?
Am I not doing that now?
No, we're still on the original.
Oh, well, thank you so much. All right, let's do that. Yeah, that's kind of an important part. Yeah, so Klein at century1.com, Kevin.Klein at solarwinds.com, and then all the social media sites at KE Klein. So Twitter, LinkedIn, Facebook, and so forth. And I hope you'll connect. So also, we don't have a terribly big crowd, but if you're interested, we could raffle off a copy of an ebook copy of SQL in a nutshell and give that away if anyone was interested in that.
Not a problem, we can do that.
All right. So in case you've never heard of me, which I kind of hate this slide, but I've been in the business since the relational database business since the mid 80s when I worked for NASA. Part of the team that put the air and water recycling in place in the International Space Station. And I also worked on some Hubble projects as well during those days. I went on to very large enterprises, leading their data management and architecture teams. And during that time, I was tapped to be one of the original 9 people who founded Parse, which had a really bad year in 2020, is now being reorganized as a foundation by Redgate Software, and they're doing a good job of carrying that legacy forward. And then also, I've written many books over the years. My best known book is SQL in a Nutshell, out of 11, and I'm currently working on a new edition for SQL in a Nutshell. So we'll be up to the 4th edition of that title pretty soon. Microsoft Most Valuable Professional since 2004, and I write a column every month for the Database Trends and Applications magazine. That's dbta.com as well. So also just want to mention one thing about the company I work for as well. We have a lot of really neat and free resources. So we have the website sqlperformance.com, which has fantastic articles, really, really good articles. We have centralone.com/resources, where we have ebooks and white papers and things. Another one that's not on the list is centuryone.com/webinars. And that is where we have webinars like this one. So I believe there's an earlier version of this presentation posted there as well. Lots of query tuning videos, lots of DBA best practices videos as well. So I encourage you to take advantage of those. So the genesis of this presentation was I had a lot of people asking me, why do relational databases act the way they do? And so that's what I set out to do originally, was to answer that question. And the first few generations of slide decks that I made had lots and lots of words, lots and lots of bullet points. And what I learned at that time was that it's hard to remember 1,000 facts. So I tried to reconstruct this whole presentation as a kind of a narrative, and to tell a little bit of a story and use some analogies. And that way, in all the minutia of the different facts and so forth, as we go through this, it might resonate a little bit better and stick a little bit better in our heads. And so I'd love to hear your feedback, whether you feel like this helped or hurt in that approach. We're about to get into the internals of SQL Server and the architectural components of SQL Server in just a moment. But the thing you need to realize, if you have never had training in relational databases, you just jumped in and started working with relational databases, is that they were developed, the theories around them and the academic kind of research that went into them, they were developed in the 70s in answer to a wide variety of problems that enterprises were having with the existing data processing systems of the day. They didn't call it information technology in the 70s. They called it data processing. And they meant basically doing what math crunchers like scientists and mathematicians do, doing that really fast, and then doing what accountants do really fast. And what the people writing these massive systems in COBOL or a codicil or a network database or some hierarchical database, some of these other kinds of structures that they had designed in the 60s and 70s, what they were finding out is people don't like it when you lose track of their money. They get really upset about that. And so banks were running these massive batch processes entirely in COBOL, and it was possible for the way these transactions were batched and run that, let's say if the power went out, they could lose some transactions and not know what happened to your money. It's just lost in the ether. And so the theorists who came together to start putting together the underpinnings of relational databases using relational algebra and relational calculus, and also something called set theory, they said, okay, we have to predicate everything that happens inside of this relational database as being the antidote to all the problems that we had with the older models. So they came up with this acronym called the ACID properties of transactions. And it stands for four things. First of all, A is for atomic. And what this means is, you take a look at the way chemists view the world. We have things like compounds. So like in my case, I have a soda here, it's tonic. And so that's a compound. Or if it was a glass of coffee, of course, or a cup of coffee, that would be a compound. Then we have molecules in there. So we'd have like sugars of different kinds. We'd have different milk fats, because I take cream in my coffee, lactose, lactase, and other kinds of things. We'd have H2O, we'd have water, we'd have caffeine, my favorite molecule. And then the next smaller organizing structure is the atom. So with an H2O molecule, you have hydrogen and oxygen. You can continue to break those particles down smaller and smaller. There are things smaller than atoms, but the atom is the smallest level you can go at which it has distinctive characteristics and properties. And so the idea here with a transaction is that it needs to be atomic, like a chemist would define it, meaning it has its distinct characteristics, like carbon is very distinct from oxygen, and it only is that one thing. So in a relational database, you wouldn't use a delete statement to also change values. You would only use a delete statement to delete records. Okay, so that's the first property. The second property is that the transactions must be consistent. And just like the word says, that means every time you issue a specific given transaction, it returns the exact same results and it always works the same. Believe it or not, systems that existed before that couldn't guarantee consistency necessarily. Another acronym there is isolated. So I always like to joke as an example of isolation in a transaction is I have one son and 6 daughters, and now my youngest is just got half a year of high school to go. So they're all high school or college age or older. But I had 3 girls in college at one time, and you know, if they had they would go to a cash machine to withdraw cash, and under the old system, the old way of doing things, if 2 or 3 of them went at the same time to withdraw money, it was very possible that all 3 of them would get $100 out of the cash machine, even though there was only $100 in the cash machine. And then I would end up getting, you know, a couple bills with overdraft fees on that, because the systems, the older systems, didn't guarantee that when a person started a transaction, no one else could affect the records that they were acting upon. See, that was a situation where they were not isolated. So isolation means that you can complete your transaction without any interference from any other users of the system. And then finally, and most importantly, they have to be durable. So that means if my daughter went to the ATM to withdraw some money, the cash machine, and a bolt of lightning hit it, there's typically in these banking systems, there's 2 transactions. There's one transaction that says, I have put $100 into her hand. And then there's another transaction that says, I have deducted $100 from your account. And so in a case like this, if the lightning bolt hits before money has been given, then it completely rolls it back as if nothing had ever happened. On the other hand, if that lightning bolt had hit at just a slightly different point in time where the money had been dispensed, it would roll that transaction forward once the system came up, so that it would always either be fully committed or fully rolled back, and that's durability. Interestingly, as we get into the details of the internals and architecture of SQL Server, each of these ACID properties represents a different architectural component inside a SQL Server. And the further down the list you go here, the more overhead and the more processing resources it consumes to support that transactional property. So atomicity is pretty much controlled at the parser level. Consistency, again, is probably at the parser level, query optimizer. Isolation is the entire locking engine, right? And locking can really slow things down. And then finally, we have durability, which is the transaction log. And if you can't write to your transaction log, you can't write any transactions, right? You cannot do work, except you could read data, but you couldn't do any writing of data. And so, in fact, I remember kind of laughing about how MySQL was picking up, and it's a great fanfare at the .com bubble. And one of the things I would laugh about was that in those very early days of MySQL, people are like, it's so fast. It's like, yeah, it's fast because it doesn't have durability. It didn't have transaction logs back then. And by the way, different database systems implement these different ways. So for example, Oracle has durability through 2 different mechanisms. So we, in the SQL Server world and in Sybase, we have the transaction log, but in Oracle, they have an archive log and a redo log. And so they have different purposes in sustaining the the ACID properties there. There's some other reasons we have architectural components inside a SQL Server. For example, getting the most out of the performance, out of the subsystems, so like maximizing the hardware, making things more scalable, better performance, all of the new stuff that has come along in the last couple of releases around in-memory optimized tables and things like that. Another reason is because Oracle has it, or maybe MongoDB has it, or some other database system is catching a lot of attention in the marketplace, and so Microsoft doesn't like to lose in the competitive arena of ideas, so they quickly will bring on new features just because somebody else is doing it well. An example of that might be, say, graph database or column store. And then also I want to point out, compare this to all of these NoSQL databases that are increasing in popularity. For example, MongoDB or Cassandra or Microsoft's own Cosmos DB. They are not built around the principle of ACID transactions. They are built around something called the CAP theorem. And that means consistency, availability, and partitionability. Partitionability in this case means how scalable across how many nodes you can ramp it up, a Hadoop cluster across 5,000 nodes or something like that. However, with the CAP theorem, typically you only get 2 of the 3. And again, think of the time they were developed and the kind of context under which they were developed. They were developed to be globally, to support global data platforms like Google, like Yahoo, like Facebook, and so forth. And so the idea that it has to have a transaction that is immediately worldwide consistent, not one of the driving philosophies of what we're trying to do, right? We're uploading cat pictures on Facebook, and we want our grandma halfway across the country to be able to see that cat picture eventually, but it doesn't matter in the same way that losing a few $100s because of a transaction that went astray. So remember ACID and that acronym. We're not talking about hydrochloric acid or sulfuric acid. We're talking about the acid properties of transactions. Okay, that drives everything you're going to see from here on out. And as I mentioned, I wanted to try and make this a little bit of a narrative so that this tsunami of facts about how these internal components are arranged and how they work and what they each do makes it a lot more memorable, a lot more easy to understand. So I'm going to use Sheldon Cooper here, and Sheldon is going to be our user, a user of a database, except I'm going to use an analogy. Imagine these are all of the different architectural components inside of a SQL Server database. And some of this is kind of lightened up a little bit to improve the narrative quality, but a lot of details in here. And so Sheldon will start here and work his way around these neighborhoods. So imagine Sheldon Cooper is in Manhattan, let's say, or any massive city, and he needs to go somewhere. Out on the streets, there are different, very small kinds of things to interact with, like maybe a newspaper stand, or maybe a little tiny kiosk where you could get a soda or a candy bar, or a slightly bigger kiosk where they sell flowers and you can actually walk in and purchase something there. But most everything is outside, right there on the sidewalk as you walk by. However, at the bottom, these are actually fairly big buildings. Okay, Transaction Manager. That's a big structure with a lot of heft to it. And then right in the middle, we have the dominant high-rise buildings. We've got the transaction log, the database file or files, and we've got the buffer pool, which is Windows RAM, and it's divided into a bunch of different caches. Okay, so think of these as like high-rises, really big buildings. And then everything along the top in red, these are really small, trivial, tiny buildings. Over here in a deeper crimson, we've got these kind of slightly larger, but very, very quick and easy kind of buildings to visit. And then finally, we have these other larger buildings that Sheldon will have to visit on his trip out into the city. Okay, so let's say Sheldon is going to write a query. And by the way, this works the same on Azure. It works Azure SQL databases. It works the same on SQL Server itself. Express Edition, Enterprise Edition, all that stuff works the same. So Sheldon steps out of the lobby of the, oh, by the way, I do have these colors coordinated for a reason. This along the top, that's circled there, and then over on the right-hand side, that's what we would call the relational engine. And the reason in the metaphor that I say that these are very tiny buildings that are quick and easy to interact with is because they actually all reside pretty much in memory. And so all it takes to utilize these architectural components is just a few CPU cycles and a little bit of memory, and then Sheldon is done with those. He's able to move on. However, down at the bottom, we have what is popularly known as the storage engine. And if you're a blog reader and you don't yet have the SQL Skills blog added to your blog roll, the principal at SQL Skills is a person named Paul Randall, and Paul was the storage engine PM for the Microsoft SQL Server dev team for many, many years. So he has really deep knowledge about this kind of stuff. But these are all physical implementations of architectural components. So they interact with not just memory, but with the disks and other parts, components of the whole stack. And so that's why they're bigger buildings, because they take so much time and energy and physical behaviors rather than all electrons like the red buildings do. And please let me know if my mixed metaphors are getting confusing, right? So Sheldon is he's in a hotel. He's let's say, for example, he's just going to write a query, and so he has to go out into the city and retrieve the information and bring it back to the hotel so he can analyze it, right? Maybe he wants to take some tours, so he's going to just take a little walk around the block and see what kind of brochures he can pick up and things like that. So in this analogy, the first thing that happens is Sheldon steps out into the world. Now, in SQL Server parlance, what we would say happens there is that a component inside of the of SQL Server called the SNI, the SQL Networking Interface, takes the transaction that he is writing and it encapsulates the transaction into, well, first it's encapsulated into something called TDS packets, the tabular data stream packets. Then the SQL networking interface, as you would expect, if you're whatever networking interface you're using, it makes it the TDS packets accessible to that. So, for example, the most common one of all, TCP/IP. So take the TDS packets and put them into the TCP/IP packets and use that protocol to send the packets out. There are other network protocols, not as many as there used to be. We used to have lots of kind of edge or small niche cases, Banyan Vines and SPX, IPX, and NetBUI and name pipes and things like that. But now the primary ones are TCP/IP, and you'll sometimes see another one called shared memory, where you're actually working directly connected to the SQL Server box itself. And so you don't even want to leave the same shared memory area because you'll get better performance that way. So SQL Server sends Sheldon's query, sends Sheldon out into the world over TCP/IP and sends him out to the next building in line. In this case, that next building in line is the parser. And so what happens, as you can see here, is something called the SQL OS, the SQL operating system, the thread management worker thread management system. It perceives that Sheldon has connected to our SQL server, probably on port 1433 using TCP/IP, and it takes and it hands his transaction, his query, to the parser. And the parser has several roles that it plays. Now, again, this is just a tiny little structure, very, very fast. And one of the things you'll see about each of these four across the top is each of these architectural components, in a way, are designed to provoke and maybe perceive kind of blatant mistakes that a coder might make in sending a query to the SQL Server, because it's better for it to fail very early in the process than it would be for Sheldon to take a whole long walk all around the city block only to find out that he has misspelled the word select, right? So the parser, that's one of its main jobs. It has a language that it understands, and it validates that syntax. If you send it syntax that it doesn't understand, you get a parser error. But it does more than that too. For example, it identifies any constants in the query code. If there's views, it will expand those out. And it also will check to see if someone has written a similar query in the plan cache and left it in the plan cache so that we can reuse it and not have to spend all this massive amount of time building a new execution plan. So what happens here is the parser will check to see, hey, does essentially the same query exist in the plan cache? And if it does, then let's use that. If it does not, so Sheldon can actually skip ahead, basically. He can skip the binding simplification, the trivial plan, the optimization. He can use that plan and move way, way ahead. But if it doesn't exist in the plan cache, SQL Server will build a parse tree. It will build a memo structure and start to populate that with information as it goes along. So that starts to pop up into the plan cache. Once it says, okay, I had to build a new execution plan, let's go to the next little building on the street. You know, you see a bunch of newspapers at a little stand and magazines. That's the binder. The binder does some pretty neat things. So before we check to make sure that we had proper syntax, but the parser doesn't actually check to see if the from clause addresses real tables or not. So the binder will do that metadata discovery and make sure that names are present. There is one exception to that, and that's if you're making prepared code, like a stored procedure. SQL Server does something called deferred name resolution, which is one of the bad things a lot of people would say about SQL Server. So that means it doesn't check the name at the time of compiling the plan. It checks the name at the time you execute it. So if you have a stored procedure that has a temp table in it, that way it will compile it just fine. And when it executes, it will create the temp table for itself. That's why it's deferred until the time of execution. But the binder basically says, okay, you've asked for a bunch of tables. Do they exist? Okay, they do exist. Do you have permissions to them? Oh, okay, I see that Sheldon has read permission to this, so we'll let it go forward. It also does things like data type resolution. So if you have any of the set operators in a query, for example, union or intersect or minus, it makes sure that in ordinal position of the first query and the second, possibly the third query, each ordinal position of the columns referenced in those have to have the same data type. They don't have to have the same name, but they have to be compatible data types. It also does aggregations or binds the aggregations at this point. And then, just as before, it takes and updates the details that exist in the plan cache with the latest information. Now, simplification is also a really neat step. And by the way, if you're curious, I actually do have demos to show all of these things. And there's a few people on the call who have been around long enough, like myself, to remember when some of the simplification code was added to the engine. I believe it started to come in around SQL 6.5, SQL 7.0. I'm sure, Greg, I'm sure you know a lot about this too. But one of the things we used to do back in the old days is if we were writing a big query in which we had a join, we would sometimes go and say, oh, you know what, I can rewrite that as a correlated subquery, and you might get a very, very different execution plan. Well, that really doesn't, it can happen occasionally, but it doesn't happen nearly as much as it used to, because the SQL Server team put in this component called the simplification, in which it looks for things that happen a lot that I can simplify and rewrite in a way that's easy, makes it a lot easier for the optimizer. So converting subqueries to joins, we can switch a inner join to an outer join, or transform it to a left join to a right join. And we also do things like remove redundancies. So if we have the same join referenced twice, in the old days, it would actually try to process that kind of stuff twice, or at least make it work harder. And now it won't do that, because the simplification engine will say, oh, you know what? I don't need to reference this join twice. Or another thing, for example, is something called contradiction detection. So you might have a foreign key to another table, but that foreign key also has a check constraint, and it says any value entered into this foreign key that's an integer has to be greater than 10,000. So if someone were to type in a query and it said where this foreign key constrained column is less than 10,000, it would see from the metadata that the foreign key is violating that constraint. It's contradicting it. And so therefore this query is going to fail. I'm not even going to bother to go beyond this. Okay. So that's a simplifier. And again, it updates the object in the plan cache, the execution plan details. It's not actually an execution plan yet. But then we move on to the stage for trivial plan. And trivial plan is basically the last step before we go into full optimization. And SQL Server now, believe it or not, it hasn't really looked at any of the metadata that exists. So you probably have heard about, and if you're an advanced SQL developer, you know intimately that indexes are extremely important for how SQL Server can get good speed out of performing a query. Well, when we're at the trivial plan stage, SQL Server doesn't even look at whether we have indexes or not, or whether it has good statistics, what the histogram has to say, the cardinality estimates. What SQL Server does is it looks and it says, okay, this plan or this query is so simple, there's basically only one real way to solve it. For just the most simple of examples is you have a table that is a heap, i.e., it has no clustered index. The only way SQL Server can access data from a heap table is to read the whole table, a full table scan. So if you say, give me these several columns from a heap table with a where clause, it will always have to do a full table scan on that. Trivial plan, doesn't have to think about it. I'll just go ahead and do that. Why bother with all the extra work here? And so that if it can find a trivial plan, again, that's a shortcut for Sheldon to kind of skip a whole bunch of neighborhoods on his way around the city. Now, after that, Sheldon turns the corner, and now we're in slightly bigger buildings, but they're still tiny, right? They're still out on the sidewalk. So maybe it's a little food vendor, and they have a couple seats around their little wagon and a couple umbrellas to keep the sun off you. But it's all just right there on the street, super fast, easy to walk past if you don't need anything. And once we get to this phase, the next thing that needs to happen is, okay, it's not a trivial plan. That means we need to know as much as we can about the context, the metadata of this given a set of objects in this query. So we need to look at things like index statistics. Maybe there's been some auto-created statistics, and the histograms that are a level deeper than that. We need to look at the cardinality estimates, which are just a fancy way of saying the expected number of rows. We also have to look at physical aspects of the server, like how much memory does it have and how much CPU does it have. The reason for that is because SQL Server gives memory grants in accordance to how much memory is available in its total. It gives CPU for parallelism in accordance to how many CPUs that it has available to it. And then there's other things too, like if you have used a set option that's different than the way the server is naturally configured. So maybe for this one query, you said set ANSI nulls off. So SQL Server will have to take that into account. Or maybe you've got a very different collation and language setting than on your workstation than what's on the server. That is taken into account as well at this phase. And again, the parse tree, the memo structure, the execution plan is updated. Now SQL Server says, we're going to do some real work here. So one of the things I need to do is to reduce the amount of records that I'm going to carry through this optimization process as much as I can, right? So if we have like a 4-table join, and each of the tables has 1 million records. And if we start with joining table A to table B, and it only eliminates 30,000 records from those 2 tables, that's a lot of records we've got to carry through and store in memory. But on the other hand, if we start by joining table D and C together, it leaves us with only 30,000 records instead of 2 million minus 30,000, like with the first 2 tables. Now we have 2 million records reduced to just 30,000 records. Well, why don't we do that join first so that we have that much less data to carry through the other phases of the query processing? So that's the, and actually, I have another session that goes into really deep detail if this is interesting to you. SQL Server uses a couple different relational algebra properties to process that. So if you remember from algebra, you remember the commutative property and the associative property. It applies those algebraically to the tables. And that's how it does its join reordering. There are, and I mentioned this earlier, there are little nuances that I'm not describing in full detail at each of these different steps. But this is, the general flow of how things work. So the next thing that needs to happen, and here's the reference to the other session I mentioned that has all the deep details about the number of joins and how that's calculated. If you go to century1.com/K-Klein, you can see that presentation, download it, and so forth. Okay. So once again, updates the parse tree and the memo structure, and then Sheldon gets to move along to the next step, which is the query optimizer itself, the query processor, you might say. And SQL Server has 3 main phases, I guess you could say. There's actually a lot of different terms for, you'll see it called a search phase or a search or a probe. You'll sometimes see it called a probe. The interesting thing, to me, the interesting thing here is that SQL Server is not looking for the best execution plan. SQL Server is looking for a good enough execution plan. So the idea is to compare every plan alternative to every other plan alternative. That's the only way you can truly know what's best. But we don't have time for that. Let's just take the first good one we come across that's good enough and just put that one into play. So that's what SQL Server is looking for here. And the way it does that is in this 3-phase process, phase 0, phase 1, and 2. And the first 2 phases use plan matching kind of technology. In other words, it's looking for a basic shape of the different operations that are going to happen. But when we get to phase 2, SQL Server inverts that, and instead of trying to match the query that you've executed against the shape that it might take, SQL Server instead says, okay, I've got this crown jewel of SQL Server, the optimizer costing heuristics, and there's more than 7,000 of those. Instead of trying to match what I'm doing to that, what I'm trying to do instead when we get to full optimization phase 2 is I'm pruning off different branches of these costing heuristics. So for example, data types like varchar max, var binary max, or char max, anytime you have those max data types, they require special handling. Any of the large object, binary, they require special handling and special optimizer rules. So SQL Server will say, you don't have any max data types, so trim all 300 of those rules off. All right, let's take a look here. Do we have more than a certain number of joins? Yes. We have more than 12 joins. Okay, we're not going to bother to do a full set of heuristics to match all of the different table join orders. We're just going to apply costing rules to those joins rather than actually reorder all of them and see which one is best. So it's an interesting way that it works. So what we have is phase 0, which is also called a transactional plan. The idea here is this is a singleton insert or a small, easy select statement, or maybe an update to a few values, like you would use in an OLTP transaction processing system. And so they're typically small. Maybe they have 2 tables in them. Okay. A quick plan is it has more rules, and it is able to match more patterns. And these are things like the most common patterns. Like I think it allows up to 3 or maybe even 4 tables in it. So you might have a query that has a couple subqueries in it in the select item list. You've got a join, but nothing terribly sophisticated, really. In fact, if you watch your in Plan Explorer, which I will encourage you to use, or in Management Studio, it's pretty rare to see SQL Server use phase 0 and phase 1. It does happen, certainly, but a lot of the times when SQL Server says, this is a pretty big query, it usually will jump to a full execution plan. And the full plan is for at least moderately complex queries. If it's got parallelism, that's always going to go to phase 2. If it's got indexed views, or you've got a group by statement with a halving clause, all of those conditions are definitely going to invoke phase 2 level of optimization. Okay. So then SQL Server says, okay, I've built a plan for you. Now let me update that in the plan cache. In case somebody else wants to execute a very similar query, we've got a good plan. From here is where it starts getting a pretty good deal more expensive as well, because you notice these buildings, they're changing color, it's getting denser, they're getting bigger, it's more overhead. One thing also that I will mention too about the plan cache is that it is hashed based on the binary of the query. So maybe you've got a team of developers and some of them like to use camel case in their queries and some of them don't. If your 2 queries to the human eye look identical, but one of you has written uppercase select and the other one has written lowercase select, SQL Server will actually have to put 2 execution plans into the cache, spend all this time building a second execution plan, even though to a human it's identical. The reason it's not identical to SQL Server is because it's a hash based on the binaries. And you know that a binary uppercase S is not the same as a binary lowercase s. It's a different binary string. So SQL Server doesn't find a match in that case. All right, so now let's, go in the wrong direction there. Let's move forward. So now we're getting into the storage engine, and this is where it gets a little bit more time intensive, and it takes more time to resolve these different architectural and internal steps as Sheldon is walking around the neighborhood. So what happens next is the access methods, okay? And the access methods, it's a collection of code that figures out how to best get data that is stored in the tables and in indexes across partitions, all those kind of structures inside the system there. And it figures it out, but it doesn't actually do the retrieval itself. That's done by the buffer manager, okay? So what happens here is the access methods figures out how physically I can get to this data. And it takes a look at things like the page free space list. It looks at things like IAMs and GAMs, that's the index allocation maps, global allocation maps, and other structures. So it's figuring that stuff out. And then SQL Server is handed over to the transaction manager. It has 2 main components, the log manager and the lock manager. And this is one area where SQL Server differs greatly. based upon the kind of transaction it is. If it's a read transaction, SQL Server doesn't have to invoke the log manager. And so what happens here is SQL Server says, okay, it's a select statement, so readers don't block other readers with a read transaction, but writers will block readers. And so we need to invoke the lock manager. And so this is kind of like a traffic intersection that Sheldon has to cross. And with read transactions, it's one of these nice intersections where there's a button and the traffic will stop for him, and makes it easy for him as a reader to get his work done. So it is a blocking operation. The buffer manager then says, okay, where am I going to find this data? It looks in the data cache for, again, using the different kind of signposts for the IAMs, the GAMs, the SGAMs, all these different little structures. And it looks for the data pages that it needs to answer the query. There's a very good chance, the bigger your database is and the smaller the amount of SQL Server memory you have, there's a very good chance that the data you need will not be in cache. And so what SQL Server then has to do is it has to send a request out to the database files to get that data, finds the data in the 8K data pages, and loads that up into the cache. Okay. I used to say inaccurately that under such and such a circumstance, SQL Server would work directly against the database. Well, the truth is SQL Server doesn't really ever go directly against the database. What it does do is it gets whatever it needs from the database and puts it into cache, and then it manipulates it there. Okay. So once the pages that he's asked for in his select statement are returned, he can, read that data from the cache and, cross the street. At that point, SQL Server will issue a transaction complete, a done in process message, and he's able to finish his transaction. On the other hand, if it's a write transaction, this is where things change up quite a bit. Okay. The first thing is that the plan cache, the execution plan in the plan cache, has a very good chance that it's going to be a heck of a lot bigger than a query, a select statement that did the exact same data, touched the exact same data. So let's say Sheldon wrote a update statement and he wanted to update certain columns in a table. Compared to just moments ago, he ran a select statement to make sure he was getting just the records that he needed in the join and the where clause, right? Well, what happens that makes the plan in the plan cache so much bigger for write operations is two things. The first is, well, you don't have triggers on select statements, but you can have triggers on updates, deletes, and inserts, right? So SQL Server's got to put that code somewhere. It's got to go into the execution plan. That's the first thing. The second thing is, think about an update. If you're writing on the writing data to the AdventureWorks database, and there's a sales order header and a sales order detail table, and so you're writing detail records in the sales order detail table, and the first thing it says is what is the product ID? And you type in the product ID. Well, SQL Server is not going to let you just type in any old number. It's got a foreign key constraint to the products table. And so it checks that constraint. However, what is that in operational terms inside of SQL Server? That's a select statement against the products table. So it has to incorporate all of this logic, all of the plan steps, plan operators to do a select statement against the product table. And then in the header, there's the salesperson ID and there's the customer ID. So it has to write queries to those to make sure those are valid people. And then it has to look at the inventory to see if the inventory levels are right. So there's all kinds of relational integrity, check constraints, foreign key constraints, unique constraints. Each one of those is a select statement. So you'll see that the plan cache will be a lot bigger if you have, a lot more bloated if you have a lot of write operations. That's normal, but sometimes it's alarming if you're used to tuning select statements, and then you start to tune updates and deletes and things like that. You're like, why is this execution plan so huge? Well, it turns out it's because of all those constraints of different kinds. Okay. So just wanted to mention that passing detail. So just as before, the access methods figures out where the data can be found, what tables, maybe if there's indexed views, also called materialized views, or across different partitions. And then Sheldon will move on to the transaction manager. But this is where, I forced you to listen to me talk about ACID. This is where ACID really gets to be a kick in the pants. Not a fun one sometimes. We've got a traffic light here at the transaction manager, and it has two subcomponents. It's got the lock manager and the log manager. Log manager is not so bad, but that log manager says, you know what, this is a write operation, and I am forbidden from letting any transaction get written to this database without guaranteeing that the transaction is durable, right? If the server gets shut down or explodes or the power is disconnected, that transaction either goes all the way in or not at all. So in SQL Server, that's typically going to be the transaction log. So what happens is the transaction log is writing serially one record after another to that file, the transaction log file. And as that goes along, Sheldon has to wait for everybody in front of him to finish that process and his own transaction to get written to the transaction log before it releases that kind of wait on the transaction log. Once that wait is released, then the buffer manager says, okay, where is the data that we need? So it says, okay, lock manager, I need you to issue, this time, exclusive locks on the pages that we're going to change. Again, they may not all be, there's a really good likelihood that they're not all going to be in the cache. So in that case, let's go out to the data files, find the various 8K pages that we need, and then load them up into the cache. And once we have them up in the cache, that's when we can actually change the data on those 8K data pages. But we're not actually done, because the 8K data pages in the data cache have been changed, but they have not been hardened, if you will, to the database file. Anytime we have a 8K data page in the cache that is different than an 8K data page in the database file, that's called a dirty page. I don't know why they chose that name. But it's a dirty page. And so there are some other processes that have to happen before this transaction actually is finally written to the database files. So typically we're going to look for something called the checkpoint to happen, at which SQL Server will not flush, because those pages can still remain in the cache. What it does is it hardens all of those 8K data pages that are dirty to the database files, and then it comes back and marks them as clean. So now they're clean data pages in the cache. And at that point, we get the done in process message, and Sheldon is returned to by the thread manager and is able to start his next transaction. So he starts out at these little small buildings, checks the parser, the binder, the simplification. Maybe it's a trivial plan. If it's not, then we've got to load the metadata, do some join heuristics, and then we do the 3 steps of the query optimizer. Query optimizer then takes us over to the storage engine, where it figures out the access methods. It figures out the best way to get to the records to lock them. And if it's a write operation, it hardens the transaction to the transaction log. And the buffer manager takes care of all of the movement of the data between the database files and the data cache. Okay. So before I go on, Warwick, do we have any questions at this point?
We've got a couple of questions. Let me just scroll back. One we'll wait till the very end. So this one's sort of been answered, but you could have a stab at it as well. Is there like a dirty dozen of bad SQL practices that all SQL devs should be made aware of, coding practices that they should consider?
Great question. Very, very good question. And it's one that Dr. Lowe, Warwick, myself, Martin, any of the MVPs that you might run into, we all have our own slide deck or three about this kind of stuff. And so, yes, I actually have a presentation at century1.com/webinars. I'd encourage you to take a look at it. And it's called Top 10 Mistakes. No, Top 10 Techniques All SQL Developers Should Know. Also, it's probably not in a reasonable time period for you, but if you've heard of the website MS SQL Tips, I and my colleague Tom LaRock, we are doing a webcast tomorrow, the 27th at 11 a.m. Eastern time in the United States, so probably too early for you guys, but it'll be recorded and available for you to watch. And it's part of a two-part series. We've already done the first part about how to design indexes well. And the second one that we're doing tomorrow is about ways in which you write code that can make indexes really useful and valuable, or can totally shoot them down and make them useless. So one example, just to kind of whet your appetite, one example is that if you have a where clause and it says where this and such column equals a value, right? So where hire date equals January 1st, 2021, or is greater than or equal to January 1st, 2021. And there's an index on the hire date column. That search argument will work beautifully to do a range scan, find the first value at January 1st, 2021, and scan forward and get you just the records you need. However, a lot of folks don't realize this. If you use many different kinds of system functions, or if you've used a user-defined function that maybe you or someone on your team wrote, and you put that on the search argument column. So if even simple things like is null, you could say, so if hire date is null, then make it January 1st, 2021. Well, it won't actually truly use that index. It might say index, you might see an index related operator there, but it's always going to be an index scan rather than an index seek. And so, that's one of those kind of dirty dozen sort of things. It's like, always make sure that you don't put those function calls onto your search arguments. And you might say, well, how would I handle it? I need to make sure if there's a hire date that's null that I have handling for that. Well, I would encourage you to think about using something like dynamic SQL, where you'd have a parameter. So if the parameter is null, then you could check for that. You could have a default value in the parameters for a stored procedure. There's just a lot of different ways to get around that. And yeah, so lots of webinars as well on century1.com/webinars that also just go into other kinds of query tuning aspects like that. So there's probably 50 things or more on the SQL Century website.
Thank you, Kevin.
Thank you. So I have some other slides to dive in on, and they're just to take us a little bit deeper. So, tell me if we are running out of time or something you don't want to discuss. But two things I thought I would dive into in greater detail, because I find that a lot of devs that I work with, even DBAs I work with, don't know these kind of basic functional behaviors. And so when they run into problems they're trying to troubleshoot or performance tune, since they don't know the fundamentals, they don't know why it's not performing the way they expected. So the two things that I have after this are, how does SQL Server keep things in memory? And the second part came in up here on